Good afternoon, everybody. This is the ECE 473 final project by Lutulu Mbiye, Brendan Ferracciolo, and Ethan Pellegrini. Project overview: we designed something we call the BLuE RTOS. B for Brendan, L micro symbol for Lutulu, and E for Ethan. It's a homebrew real-time operating system that we did for the class. It's a fully functional operating system similar to Micro COS2. It was used as a really good reference point for everything we did. So everything that's really important about this is our cooperative scheduler. It runs at max 10 tasks by default. It uses semaphores, flags, mailboxes, with an API system similar to Micro COS2, and it kind of fixes some of the quirks in COS2. Like, we have an easy to initialize baud rate for our UARTs, and some of the device drivers have been rewritten so that you can use both Tiva buttons instead of just the one.
For our context switcher, that was easily the hardest feature of our operating system to implement. So we'll go into that in significant detail. The switcher is split between the C code and the assembly code. To start, the timeout on a task expires, and that triggers an interrupt to push the task registers onto the stack. It then loads the scheduler's task pointer, pops the scheduler's registers off its stack, and the scheduler then selects the next task. And then it pretty much does the same thing in reverse. So it pushes the scheduler's registers on the stack, loads the next task that the scheduler selected, pops the task's registers off its stack, and the next task continues where it left off. For switching between C and assembly, we use global variables. We used the extern keyword to import one into the other, so functions and globals from C and subroutine labels from assembly. And then we also use the export keyword in assembly to make its subroutines available to C. As well, we didn't really use it in the context switcher, but certain other functions use it, that assembly instructions can have data passed in or returned via register 0. The context switcher has to push and pop all the CPU registers, and there are quite a few of them. Unfortunately, half of those registers are very difficult to save onto the stack, and that's why we use a pend SV interrupt to handle our task switching. And that is because when the interrupt is triggered, this first set of registers is automatically pushed onto the stack. And then within the interrupt, we can push the rest of the registers. This is the assembly code for the first half of pushing the registers onto the stack. So as you'll remember, the delay expires and the interrupt triggers. Then we disable interrupts, push that second set of registers onto the stack. We then load our current stack pointer. This is a value from C into R4. Store the stack pointer into the global variable, so this can be used later. We then load the address of toReturn which is another subroutine we'll get to later, into the link register, and then we branch to the switcher. And the reason we load this into the link register is that when we branch to switcher, the link register isn't updated. But when switcher, which is a C function, returns, it'll jump to whatever's in the link register, and that's our subroutine in assembly, which is this subroutine. So to next task will handle the rest of the switch. So it'll load the stack address of the next task, load the new stack pointer, pop the set of registers that we are able to easily control off the stack and into the registers, and then it'll enable interrupts and return to the normal functionality, which in this case would be jumping to the scheduler. To jump back to a task, we do pretty much the same thing in reverse. So we call those same two assembly subroutines and the switcher function, but instead of going to the scheduler, we go from the scheduler to another task.
So from here, we're going to move on to semaphores. As stated earlier, it's pretty intuitive with COS2. So our API, for example, for creating semaphore is create sema, where you input a semaphore and it'll assign it a value, a count value. The next one is going to be pend sema, which takes in that semaphore with whatever count value you had assigned. and will essentially decrement it to symbolize the acquiring of that resource. Except sema queries the semaphore and it returns 0 if it can access the semaphore and 1 if it can't, meaning that if the count is 0, it's going to return 0. Otherwise, it'll return 1. And then finally, there is post-sema, which is used to signify that the task is done using the semaphore. So it'll just increment the count of the semaphore. And then it'll unblock any tasks previously blocked by that semaphore. Flags. Now flags are almost identical to semaphores in the way that the APIs work. So we have create flag, which initializes the provided flag with the provided mask. There's only flags enabled with the mask can be used. We have a penned flag, which it basically checks if the bits are set on the flag. If not set, the task is going to block. Otherwise, it'll take the bits if consume is 1. So it'll literally consume the flag bits. We then have accept flag. So what that's going to happen is it is basically the same as pen flag, except if the flag is not set, it'll return an unsigned integer of 1 instead of blocking. So this is really good. It works really similar to a query. And then finally post flag. Post flag sets the mask bits of the flag to 1, and it'll unblock all of the tasks blocked by that flag. If the flag bits of the mask are not enabled and are attempted to be read from or written to, the function is going to return with an error of 404. So we then move on to mailboxes. We start, of course, with the create mailbox, which will initialize the provided mailbox. We move to pen mailbox, which will accept whatever message has been sent via the mailbox system. Now, if the mailbox is empty, however, it's going to block the task that's trying to access it. Next is accept mailbox. It's basically a non-blocking form of pen mailbox. It's more of a query. Next is post mailbox, where it writes mail and sends it through the mailbox to whichever other tasks are receiving it. It's really, really important to note that it sends a void pointer. This means it's going to have to be typecast as it's received. The next two APIs are simply to test if the mailbox is empty or if the mailbox is full. This will make it easier to not have a task being blocked.
To demonstrate our operating system, we recreated Lab 5. This is a lab we were given before this one where we generate random blink rates for the onboard LEDs when the onboard buttons are pressed. It demonstrates the use of mailboxes and flags, and it'll also print the system status information. So as you can see here, it will continuously output the system status of the operating system until a button is pressed, in which case it uses that flag and mailbox system to safely update the blink rates and output the updated information to the console without conflicting with the system output information. That system output information will pause as the updated LED information is displayed before continuing. Thank you for your time, and go BLuE.